I think we can start now. So, hello and welcome to all. My name is John Favaro. I'm from Trust IT and from AI Sprint, of course, and I will be moderating this webinar today. So we have the luxury today of being able to do a deep dive into a single topic. We're going to look at a single use case of the AI Sprint project, which is concentrating on transforming wind turbine maintenance by unleashing the power of artificial intelligence, as our title says. So first, we will have an introduction to AI Sprint, where Danilo Ardagna, the coordinator, will not only introduce the project, but also set the context in which our wind turbine use case is positioned to help us understand the big picture with respect to the project. Then we'll hear from our two protagonists. Michał, the technical use case lead, who will be speaking a bit more about the technical context, and Edward, who will be speaking with us perhaps a bit more about the business and the user point of view, let's say. And then we'll have an interactive user session moderated by Rita, and a question and answer session. A quick word about who is online with us today. As you can see, the largest segment of the audience today is AI application developers, which is very interesting indeed. So I expect to get a lot of interesting questions from you to our speakers today. Speaking of which, a couple of words about housekeeping. As I said, there will be a question and answer session at the end, but you are most welcome to write questions and comments at any time into the Q&A box that you should be able to see at the bottom of your screen. Or if you can't find it, which sometimes I can't do either, just write them into the chat. In any case, we're looking forward to hearing from you. The more questions, the better. So we'd like to start the program today then with Danilo, who will present to us the AI Sprint project. So Danilo, I will stop sharing now, and the floor is yours, so to speak. You are muted, remember.
Okay, sorry. Welcome also from my side. I'm the scientific coordinator of the project, and I'm associate professor at Politecnico di Milano. Actually, our project, as in the title, has a focus on supporting the development of AI applications at the edge of the network. We started actually really taking a look on one side on the AI market, and on the other side also to the edge market that, as you see here, are characterized by a very significant growth. And today AI is, is in the news almost every day. But there is a general consensus. AI covers a really different application, but there is a general consensus that the most innovative applications will really happen because of running the AI at the edge of the network, where actually the latency can be reduced, and we don't depend on the continuous connectivity also to the cloud data centers. However, given this fragmented deployment of the applications, what happened is that there are some more challenges which are due by the fact that the devices, the resources are really heterogeneous, and there are some performance fluctuations in the network that connects the different layer of computing continuum applications. So the goal of our project is to support developers and system operators to design on one side of the application and to manage the application at runtime in a way that some performance guarantees can be set up at design time as a constraint that are fulfilled also while the application is in operations. So what are we doing is we are building a complex framework where we are introducing some simplified programming models in a way that AI designer can put some constraints on the device that run the application or on the execution time that need to be fulfilled at runtime by simply annotating Python code. Then there are, under the hood, there are some optimization tools that identify automatically the optimal deployment for application and trigger the automated deployment of the application into production deployment. And the production deployment is also dynamically reconfigured according to the workload fluctuation that naturally happen when an application runs. We are keeping an eye also on security and the privacy of our applications. We are providing solutions that allow to run applications securely, even when, for example, the backend components run in a cloud provider where an opponent can have a root access to the underlying resources. And finally, given our specific focus on AI, we're also developing some vertical building blocks that allows to quantitatively evaluate the privacy of the application and support distributed training through predator learning, for example. And we also support the stage of automatic optimization of the network architecture that solve a specific task. All our solutions are open source, and actually with a bit more detail, our framework relies on standard OpenStack and Kubernetes system for provisioning the underlying resources and for orchestrating the containers. Everything run is a Docker container. And on top of these standard building blocks, we have Scone, which is our solution for the confidential computing. Then we have distributed also a hierarchical monitoring system that is able to monitor all the resources across the computing continuum and is able to trigger readaptation in case of quality of service performance violations. Our inference pipelines work within OSCAR, which is a tool developed by our colleague at UPV, University of Valencia, which support actually serverless execution of components. We build on top of OSCAR a tool able to automatically profile the application and to also identify some machine learning models that allow to predict the performance of application under unseen configurations. The deployment of application relies on the infrastructure manager, which is an infrastructure as a code orchestrator of cloud resources. We can offload the applications also on AWS Lambda by relying on our SCAR solutions. As you know, also AI application can be accelerated and their performance can really improve in case of the adoption of GPUs. And we, in our toolchain, we have Arcuda that allow to access GPUs remotely. Allowing in this way to run faster the application in small devices. Concerning accelerator, we have also developed a specific GPU scheduler, which is able to minimize the training costs under public clouds, and is able to reduce the energy costs under private clouds. We have also solutions for migrating, given the concern on energy. We have Krake developed by Cloud and Data, another of our partner, that allowing, given the energy metric, given the availability of green energy sources in some specific data center, are able to migrate applications from one location to another. For what concern the design we have in our solution COMPS, which is a technology developed by the Barcelona Supercomputing Center, which actually, through simple annotations, allow to distribute the AI training and inference on multiple core or on multiple nodes. For what concern the design time, we have also a tool that supports the automatic design time exploration, which is named Space for ID. It has a runtime counterpart that triggers the adaptation in case of performance violations. We have a tool that automates the network architecture search of these deep learning components in a way that even developers without deep learning expertise, just providing a label data set, can obtain a good performing deep neural network. And finally, given the emphasis of 5G in the future generation systems, we have also a tool that supports the deployment and the security of network functions under 5G network. Everything is, supported by a simple design environment where, again, through annotation, everything is automatically triggered from the specification of constraints down to the runtime adaptation. Today, we are validating our tools through 3 use cases. One is concerned on a personalized healthcare scenario. The goal here is to develop a solution for automatic stroke identification. We have a solution which is core for the webinar today, with a focus on maintenance and inspection. And finally, we have a use case on farming for the toe, where the goal is to use AI on the field to try to limit the spraying of the chemicals on grapes, actually, trying to reduce in this way the environmental impact of the production in real scenarios. For what concern the maintenance and inspection use case, it is characterized by a complex pipeline. As you see here, we have several components. The analysis starts by taking some picture in a drone, and then these pictures are processed by components that are actually deep neural network that at the very end needs to identify some defects that are identified on the blades, for example. Here, the dotted arrows allow us to say, okay, the first component, for example, at the same time, can run on a drone with or without a GPU. Then the other components can run, for example, on a PC or an edge server. Other components can run in cloud, and we can specify, oh, look, these components before, I don't know if it is better to allocate this one in a huge flavor VM or in a medium VM, for example. And some other components can be also allocated in AWS Lambda and running as a function as a service solution. The key point is some scenarios, some deployments, there is a good connectivity. There are even 5G networks. So the optimization, given the performance constraint of this application, the optimal deployment really relies and depends on the specific condition, for example, of the network where the application will run. Vice versa, if this application is run where the blades are, for example, in the middle of the ocean, of course, there is no connectivity there. And so the optimal deployment is totally different than in the one where, for example, we are in a urban scenario where we have a good 5G connections. So the key point here is given our design time tools and our runtime adaptation tools, actually we can really simply identify the optimal deployment of minimum cost that really guarantees the execution response time of the individual components. Actually, we are almost reaching the end of our project. We are releasing our integrated tool chain really in these days, and here I'm here for inviting you to join our alliance that actually will allow you to use our tools for free with some support without any prerequisite and any requirements. So we, in our consortium, we have Cloud Indeed, which is a cloud provider, And actually, if you really need to use resources, you can access Cloud and Delete resources for free that are covered by the project. So that's really all from my side. So really, I really invite you to visit our website to see the documentation of our tools, and really to join our alliance to provide feedback and to help us in testing and validating our tools also in different application domains. The floor is yours. I don't know, back to you, John, or the floor is to Michał now.
Yes, thank you very much,
Thank you.
Danilo. So please remember about the AI Sprint Alliance. We're looking for new members, so get back to us about that if and when you like. And remember to ask questions at any time during the sessions, in the comment section, in the Q&A section, and remember that there will be an interactive session after the talks. So without further ado, we come now to our main event, in which we will have both Michał and Edward speaking together on the particulars of our use case. So Michał, the floor is now yours.
Thank you, John. Let me share my screen then. Okay, I hope everything works properly. So,
all clear.
Yeah. Hello, everyone. My name is Michał Kłosiński, and I'm Chief Software Architect at 7Bulls, also lead of the data science team there. And I'm also working with TTA for a long time already on their machine learning solutions for wind turbines and actually industrial inspection in general. Yeah, that's more or less what I will be talking about. So I will cover briefly what turbine inspection is about, at least visual part of turbine inspection. I tell you a bit about our background, what we used to do, what we are doing right now in AI Sprint project. Explain a bit what's the difference. I mean, those 2 points about our cloud data processing pipelines that we used to do or implemented in the past, and compare that to the AI Sprint flows and what AI Sprint allow us to do with our software. Finally, I will go a bit into the details of the software stack that we are running in our experiments, and how are we going to validate the AI Sprint project using our use case. So that's the brief plan of what we are going to talk about. So first one, yeah, let's have a look. Everyone knows how the wind turbine looks like. However, what is normally not visible from the place you are observing them are damages that are happening to the blades. And I put some small examples in here. However, there's much more. Normally, depending on who is doing that, there's like 20 or 30 categories of the damages that can happen to the blade. Our use case is about identifying those damages automatically from the images taken from the drone or UAV, so unmanned aerial vehicle. So yeah, that's what we are trying to do. To give you some idea, the blades can be pretty big. We are taking like 400 images even for one single turbine to cover the whole area with good details. Normally, images are around 20 megapixels. That's what kind of data we are dealing with single turbine. So that's what we do. That's what we are working with in here. Now, how we do that and how we used to do that. So first of all, we started as a fusion. It was our US startup that was doing the first cloud asset management platform. So the software that allows you to store information about your turbines in this particular case, monitor their damages, see how they are behaving over the time. So that was the start, and first step to enhance the functionality of that software was to integrate with the external AI provider, generic one, that was able to identify high level what kind of damages are there on the blade. Next step, and that's the place where I started really my adventure with this whole subject, was to have dedicated model that allows you to find bounding boxes, to be a bit more precise, but also to allow you to be more specific or flexible in the way you are doing the analysis. So our whole solution that we first implemented still as RFusion allowed to have multi-step various workflows. Those are those pictures with green fields that we are seeing on the screen. So we were able to say, okay, let's have a number of machine learning models, maybe some image processing logic that allows us to get some results and find those damages on the blades. But on some other cases, the pipelines were a bit more complex. I will go through the bigger one in the next slide. But basically, our platform allowed to change behavior depending on the location, whether it's offshore or maybe it's some desert. There are usually completely different types of damages on in those two areas. But it also might be different depending on the customer. Some customers have some particular needs that need to be addressed this or another way. So that was RFusion, and at some point RFusion was sold to some other company, but Polish subsidiary of RFusion remain as independent company. Actually, also still working with the acquirer of the previous business, and we will kept doing some with our remaining IPRs, but also know how we built some tools from the scratch actually for more or less the same purpose. And after a while, the AI Sprint came. And even though we built the new pipelines, they were still cloud-based. So it was software that allowed you to analyze the images in different various ways, focus on the wind analysis. The change that we are going through right now refers to, well, being able to change the batch processing and cloud-only processing to more diverse pipeline where part of the processing is happening already in the field, on the UAV itself, or on the edge computer, edge server or laptop that is in there, and then finally in the cloud. And as Danilo explained, those things might be moving over the time depending on the needs or some constraints that we have in given scenario. Yeah, that last picture on the right, actually, I will also go into details of that picture later on. It's our solution with AI Sprint when we are using AI Sprint tools to do exactly that. So do seamless data processing over the multiple types of resources on the edge, in the field, and in the cloud. So yeah, as I mentioned, we start from the various pipelines in the cloud. This is an example of this pipeline. It's one of the more complicated. We have this one was split into two types of processing actually. One is pretty, let's say, standard when we find candidates for the damages, we do the cropping, we do the damage classification, severity classification, then post-processing that somehow and sending to whoever asked for such an analysis. But there's also the second part, which was focused on the leading edge of the blade. So when we have wind turbine, the blade is actually like in the planes. There are 4 different faces of the blade. Everyone has a bit different properties. There's a cutting edge or leading edge, trailing edge, and high pressure and low pressure side of the blade. So because of the differences how those faces are working in practice, they tend to receive different damages. And one of the cases that we were working on was about erosion. It was offshore wind farm when you had a lot of erosion on the leading edge of the blade. And moreover, the idea of the customer who was doing the analysis, they wanted to somehow statistically assess the health of the wind farm. To do that, they were doing some math around area covered by the erosion, severity of that erosion, and also location on the blades. In the end, what we needed to do was to get exact area of the damages. To do that, we introduced this left-hand side, or at least on my screen is left-hand side. Pipeline, when we were doing next to normal analysis, we also were doing some additional semantic segmentation to get exact measurement of the area of the damages to be able to provide statistics. So that's an example. Now, what we are going to, this example was, again, batch processing in the cloud. So our example pipeline in the past was that there was a data capture done by the operator in the field. Quality assessment and data upload was done actually manually by the operator. All the data goes to the asset management application, which in turn triggers the processing or analysis of the data. So asset management is in the cloud. There's AI engine in the cloud. Once all the information is uploaded, it goes into the AI engine to do the processing, returns the results, and in the end, analyst, human, who is looking at the AI results, is doing some adjustments and preparing the report for the given turbine or wind farm. So that was the pipeline, the manual part, batch upload, batch processing, and then post-processing by the human. Now, what we are going to, it's more online processing. So we have an operator in the field. Of course, still somebody needs to start the drone and make sure it's operating properly. But already during the data capture, we'd like to do quality assessment. And that's happening on the drone. I will explain the software details in a second. But there's a model that assesses that information. Moreover, we can have some additional models working that provide additional information. In this particular example, it's blade part detection, which basically says in which part of the blade we are located. It can be used, for example, for autonomous flight as a loop closure feature, so confirming that the location of the drone is as we would expect. So that's also quite useful information to be on board on the drone, which might be fed back into the post estimation of the drone, so localization mechanism. Then, well, in case there's too much processing from some reason, we could also offload some of the pipeline to the edge server, like Danilo said. So it also can happen next to the drone in the field if there's such an option. Then we have clearinghouse and damage detection steps, which we all often combine into single model, which tells us, okay, this is completely clear image, is not that interesting. We can process that somehow later on, but basically you should not look for the damages in here. So that's a first filtering step to say which images are interesting, which are not. And again, we'd like to do such processing on site, because it means that if we want to have quick feedback on the state of the blade, we can send to the cloud only images that are interesting for us. And depending on the age of the blades, it might be like 80–90% of the data will be gone immediately because blades are in a good shape. And even if we need to send some information, we can send over the crops that are smaller than the whole image. So that's what we can achieve in the field. And then we are doing more processing in the cloud when we do final damage classification, severity assessment, and preparing the data for report generation. And in the end, of course, still some human need to take a look, use some additional software to generate the report and provide the final report for whoever is asking for it. So that's where we are going. And now the key differences, well, I talked about most of them, but what is happening in here, we used to have manual quality assessment, manual data upload, batch processing in the cloud. What we want to have after this project, after AI Sprint, we'd like to have immediate quality feedback, so operator can have alerts already during flying the drone that quality of the data is not good, the exposure is not right, lighting is problematic. On the offshore, you can often see that the light reflected from the surface of the water can really make the image pretty bright and sometimes difficult to analyze. So things like that can be catched already very early, already automatically on the drone. Then we don't have this manual step of uploading the data. We'll have rather seamless pipeline of processing, and all the data will be gradually fed into the AI engine. Of course, we might have connectivity issues, and that's, again, something that we need to take into account, that sometimes the images will be uploaded once there's a cellular network or we are attached to the internet. But in a happy scenario, like in places where we have connection and a way to send the data, we can have that immediately. Yeah, so that's what we are aiming at. And now how our software actually looks like. So we have three major kinds of processing or components, you can say. So there's UAV or the drone, which we fly actually on site. We have some notebook or edge computer, and we have the cloud. Looking at the left-hand side, so UAV, we have actually two computers on board of such UAV. One is a flight controller, or so computer that actually handles the flight itself. We normally don't do anything with that software. Well, okay, that's not always true, but most of the time we don't need to change much there. It's running some real-time OS and is simply responsible for handling all the technicalities relating to flight. However, we have also companion computer that talks to the flight controller over the Mavlink, which is protocol dedicated for communicating with flight controller. In this particular case, actually, it's not only about the flight, but generally some autonomous devices. So we have companion computer that gathers some data, can exchange some data with the flight controller. And in our case, this companion computer is running the robotic operating system. So it's actually Linux plus robotic operating system, which is a layer that allows you to do some standard operations with UAV, but also provides some infrastructure for communication and so on and so on. And then next to it, we have AI Sprint stack. And in here, we are running some Kubernetes cluster with Oscar. We are running, our company computer is an NVIDIA Jetson right now. We also did some tests with Raspberry Pi, but since we want to leverage GPU in our calculations to speed things up, we are using NVIDIA Jetson in our experiments. So we are running some inference jobs on the UAV itself. We have some monitoring node that speaks to our cloud monitoring database that also provides us some alerts about whether the processing is fast enough on the one hand. On the other hand, for example, if the image quality is too low, we'll get the alerts as well to notify our operator. Then we have the notebook. It's again, we have AI Sprint stack in here, working with communicating with the drone, getting the analysis result from the drone, and continuing the pipeline, providing us next inference results and passing the data to the cloud. So yeah, we have also Cube ground control, which is not that important, but it's a software to control the drone as well. So yeah, that's how it looks like. And of course, the cloud it's something that that is pretty obvious. Again, we also use Oscar for the inference. We have monitoring infrastructure in here, space for AI, so R. It's what Danilo was talking about regarding the optimization of the resources and processing. So what are the key elements we are using? Of course, we have some technical stuff that we are using, like ROS20, PX4, Q-ground control, SIF, Gazebo, all that stuff that is specific for UAV. But what is important from our perspective, machine learning models that we run is AI Sprint, and we are using infrastructure manager to deploy the resources. We are using monitoring for the AI Sprint. Oscar family, like Oscar for processing, Oscar P for profiling and providing the performance models, and space for AI for optimization. So those are the main components. It's probably a bit shortened and simplified list of the components, but those are the most important components that we are validating in AI Sprint and using to enhance our pipeline. And finally, how we are going to validate the components for AI Sprint? Well, first of all, we are doing some in-lab tests, some statistics, checking how fast things work and how they behave. That's actually mostly behind us. But we also want to make sure that all the components work properly on the UAV, testing also behavior of the Companion computer itself, it has some limitations. It works a bit differently than the big computers, let's say, and we are checking how it behaves mostly performance-wise, but also resolving some smaller issues. And we are more or less right now in setting up end-to-end tests in our lab test for inference pipeline. In the parallel, we are testing our drone that was built specifically for this particular task. It's pretty old image actually from the very first test after assembly. Now it looks a bit more scary. I mean, there's more pieces and it's bigger a bit, but it's I mean, geometry is quite interesting because it's unusual V shape for the UAV. That's why I wanted to show how it looks like. And in the end, we'll actually fly with all that stuff in the field, taking the pictures and analyzing the images in the field on one of the turbines in Poland. So yeah, that's in a very, very short version our use case and what we are doing here with a sprint. So thank you very much. And now I think over to Edward for more business look at the whole picture.
Good afternoon. So thank you very much indeed, Michael, for taking us through that. John, if you can kick in if there's anything that we're overrunning or anything.
Not at all.
We're okay?
Yes, you're absolutely fine. Go ahead.
Super. Well, look, let me address here a little bit more the issue of the commercial reasoning and help with some of the commercial issues involved in this project. Effectively, I'm going to probably talk a little bit in parallel with what Michael has covered on the technical side. Essentially, we introduced the fact that we as a commercial company at some point had the wind blade inspection business model, clearly understood that there was going to be requirements for image recognition, analysis of other infrastructures. So our initial use case was very much aligned to the wind turbine blade issues. We had very specific customer requirements coming from a number of vendors. And here it's worth mentioning that the customers that we were working with were two kinds. One was the producers of the wind turbines themselves. And then there were the users of those, that means the utility companies that had them installed in the field, both of them having slightly different requirements for analysis of their wind blade. If you think about it, the manufacturers offer generally a 5-year guarantee on their wind blade. That wind installed tower and its functionality usually has a 5-year guarantee time. At the end of that 5-year guarantee, the customer usually takes over the responsibility for maintaining and running his wind farm. These wind farms generally have a life cycle of about 15 to 25 years. Some are then indeed continuing after upgrades and refurbishment. And as you could imagine, a wind turbine blade has significant erosion problems from weather elements, which are even more critical once you put that wind turbine offshore. And the general trend these days is that more and more of these wind farms are going offshore, where both the blade is longer, the turbine is bigger, and it's more difficult to access it. So our initial use case was wind turbine blades. We basically had the enhanced functionality requirements coming from our use cases. And as I mentioned, there were two different kinds of customer. The manufacturer generally, in principle, wants to keep the data to themselves. They don't really want to share that data with anybody because it is it is manufacturer sensitive, while customers generally are much more open. And I mention that because the whole program with respect of AI is that having collected for each turbine some 700 to 1,000 images, the AI is used to improve the efficiency of the operator, who then has to scan through all of those 1,000 images and find the problem on the blade with respect to the damage that's occurring. And Michael did indeed mention earlier on that the typical damages are then categorized between 20 to 30 different categories, whether they are cracks or whether they are oil leaks, or whether they are variety of different damages that can occur to a blade which is exposed to the elements. If I can take the next slide, please. Now, in the discussion that's already been taking place with Michael, and we can go on into more detail on this as we go and answer the questions, the onboard processing, of course, is very critical because it allows the work that is the data that is collected, the work to be done pre-processed. The communication, therefore, between the drone and the cloud reduces. And in very many cases, we found that with the fact of the amount of data that was there, if the infrastructure for the data communication to the cloud was not good, that the images could simply not be transferred across. The images then found to be perhaps not exactly correct. And at that point, you had to have the team go back and redo the entire exercise, which is extremely costly because you've got two issues. Not only is it the cost of the team that's in the field, but you've also got the second cost of actually shutting down the wind turbine for a day while that data is being collected. Not that the whole process of the scanning takes that long, because you can usually scan an entire wind turbine in probably 2 to 3 hours. But if you've shut it down for that day, and then you have to come back another day later, that becomes extremely expensive with respect to loss of efficiency of the whole system. So the immediate image verification is a fact that was very clearly a requirement, and that is one of the issues that is key to this whole project of the print. The other thing, as I've just mentioned, is if you find that the data that is being collected is not correct, and you need to go back and repeat the images, that becomes extremely ineffective. So if you can do automated onboard processing and know that the data that you've collected is correct, that's, again, a huge efficiency factor. And then the edge computing, obviously, the faster that the data can be analyzed and computed, the more effective then the next step, which is essentially to verify what kind of repair is required to the particular blade. So the whole idea here with our AI Sprint project is to, as much as possible, improve the efficiency of the data to be processed on board the drone and reduce the amount of data that needs to be downloaded into the cloud, as well as the faster processing, because less data is indeed transferred. If I can get the next slide, please. So we started with wind turbine blade imaging, but as we started the process, very quickly we found that other infrastructures have the same kind of problem. So we have built into this whole program architecture in this generation, which allows flexibility for very quick cross applications into whether it is power lines, which have their particular issues, whether it's the fraying of the power line itself or the suspension mechanisms that are holding up the cables. Photovoltaic farms, checking to see whether the cells are active or not active or correctly working. Huge amounts of issues regarding bridges, which need to be checked on a regular basis, and several other buildings, telecom towers, and you could imagine the number of other applications that result once this technology is efficient. The whole idea of this is based upon having a library of images the AI effectively looks up a anomality on the blade, taking the blade as an example, and looks for something that it can compare that anomality with in the library that is stored of faults that have been detected previously. As I mentioned, the manufacturers are pretty sensitive to the fact that they don't particularly want their image library to be shared, because it potentially implies that there is a fault that is a design fault in the blade, whilst general users are much more open to sharing their data because they feel that they can all then benefit from the cross usage of their information. The next step, of course, in this process is taking the data that we've analyzing the fault, whether it's one of those 20 categories, and if it's a particular fault on a particular location on a blade, then the repair team will go out to repair that blade in time, and that whole process, which is essentially getting the repair crew lined up, knowing what the fault is, knowing what equipment to take with them to site to make that repair, is then the next automated process that we were looking to do with the technology, so to effectively, as much as possible, automate the entire process. So that's a quick overview of the rationale of where we were in starting with the wind turbine process. And as you can see, it's moved then into other areas. Power lines being one of the big subjects, because it's obviously a difficult utility to access. Power transmission lines usually are quite high. They're obviously very dangerous because of the high voltages that are in them. And therefore, the repeated requirement for checking whether the insulators are in good shape and so on is a next natural huge market that we are addressing. Telecom towers are becoming more and more popular, and more of them as we go into 5G and so on, in another huge area of requirements. John, I'm going to keep it to that because I don't want to overrun, and obviously much more will be available in the Q&A session. So with that, thank you very much.
And thank you very much, Ever, for this fascinating overview of the business considerations, let's say, associated with this. So yes, now we're going to segue over into the Q&A session. Michał, if you're still with us, please turn on your video, and also you, Edward, of course, turn on your video. And I have a couple of questions. In fact, I'd like to start with Edward, because I know that you may not be able to stay with us for a while. So we were talking about the business challenges of doing this, and also going over into other fields like power lines and things like that. I suspect that along the way there are lots of things that have to be solved to make it efficient, to make it work. Like, for example, just the drones themselves. Is it that easy, really, to just take a drone off the market and start using it on a completely different area?
Well, first of all, there are different types of drones, and then there are different kinds of issues with flying the drones. One of the biggest issues, additionally, which we haven't covered here really, is the automated flight aspect of drones. Yes. Because if you imagine a blade with respect of having its 3 blades on a turbine, and the fact that you're collecting something like 700 to 1,000 images, if you can do that in a way that is structured and logically done, then the data is critical to effectively identify at what point that fault occurs. Because you can obviously find a fault and then not know where it is on the blade. So you, as the drone is flying up and down the blade and taking consecutive pictures one by one on the 4 sides of a blade, the back, the front, the sides, left and right, it's very critical that you have those images taken in sequence, and that you are then able to identify how far away they are from the nacelle and how close they are to the tip. So that essentially is the way to measure where that particular image was taken. So you really want a repetitive flight sequence process. And therefore, what we found is that if you can program the drone in its flight to position it on effectively a geosatellite positioning, so you effectively arrive on site, you figure out where the drone and the turbine is, you lock into a GPS coordinate, and then you basically say, go fly, and it knows it has to go up. It needs to find the ends of the two tips of the three blades, and it then can calculate from the GPS location where it was to the ends of the two blades to then know where the three blades are, and essentially can then scan up one blade, down the other side of the blade, the two sides, go on to the next blade. And for that, you basically have locked the turbine into a stop position, and the blades are not rotating, and the drone is able then to do automated flight. So that is another very critical factor to avoid pilot error and to avoid the problems of not knowing where the fault is once it's been found.
Now, that brought to mind when you said you wanted to find out where things were, a discussion we had earlier about privacy concerns among the manufacturers. And I think you said that sometimes the manufacturers don't even want you to know where the turbines are located. So what are the kinds of things that they really are worried about? I realize this is different from personal privacy, which we're looking at in the AI Sprint use case for hospitals, that sort of thing. But what kinds of privacy concerns are there with the manufacturers? What are they worried about?
Michael, I think we had that discussion. Maybe you want to take that up, because I know we had that discussion in particular with one customer who did not want to know where his farm was located. Wanted the background to be erased when that data was collected.
I mean, the main privacy concerns we faced are two kinds of them, actually. One is what Edward mentioned, indeed, is that we had customers who didn't want for anyone to be able to identify the blades. So they were concerned about serial numbers, about any elements of the background that can identify location of the blades. And finally, of course, all the EXIF information where you have GPS location, all that stuff stored automatically during the taking the pictures. So that's one case. And it happens not for every customer, but in some specific cases from, well, the reasons I don't really know fully, but yeah, it happens. The second concern is a bit more tricky from machine learning perspective, which is because in this particular case, we can use machine learning to solve customers' issues. We can remove the background using semantic segmentation. We can blur the serial number. We can remove EXIF information that's actually simple, and we can make sure that the images are kind of private, stripped of the specific information to the customer. But the other kind of concerns relates to the fact that I think it's about competition. I mean, some companies say, okay, I will share the images with you. And actually, that's the truth for most of the cases. Please don't use that images to train your models for others. And it's tricky a bit because, of course, when you train your models, you actually want to use transfer learning, and instead of spending weeks of training, you want to do that in a few hours or a few days to have a new model. If you want to do that from scratch, or it will take forever. Of course, you can use some general models on the ImageNet or Coco or any other data set trained, and it also helps a lot. But of course, it's much more efficient to use your common basis of the model trained on other turbines and use that for the new customer. And that's not always that easy because of those constraints. So I think those are two main things that happens. And of course, in here, some tricks, some generating some data, some I don't know, some models that can help us generating the images based on other images helps a bit. I mean, we can kind of work around some constraints that customer pose on us.
Yes. Okay. What would you consider? What would be the steps then to actually do the transformation from what you're doing now with wind turbines to another field like power lines or something like that? I mean, it sounded to me like, yes, it's applicable, but there's a lot to do to actually move over to another area like this. There's different kinds, as you said, Edward, there's completely different kinds of things you're looking for. And it's a very different kind of setup. So what were the steps that you would have to do, and how could AI Sprint, for example, and their approach you're taking help to do this?
You know, surprisingly, many cases are not that different. I mean, of course, there is a machine learning aspect. If you train your models for turbines, it won't work for, I don't know, telecom towers or insulators on the power lines. But that's something that, well, okay, we pretty much know how to do. It requires data, it requires some time, computation resources, and actually AI Sprint has pretty nice tools to help you with that process to train. We as TTA, in this use case, we are not using those tools because we are using models that we already have trained for wind turbines. But in new vertical, we could use some of the tools of the AI Sprint to build new models and make the training process efficient. So that's one of the challenges. It's okay, it's pretty known challenge. It takes time, it takes some resources, but we know how to do that. What we actually benefit from in our case is that those pipelines are pretty flexible. So of course there will be different steps for different verticals. And what is important for us is to be able to set them up easily, define them easily, to deploy new setup quickly, and have some tools to orchestrate the whole process of introducing new pipeline, testing it, and providing to the production. So, and that's, again, AI Sprint has a number of tools that help with that. I mean, we don't need to worry about a lot of details, development tasks, because they are already done in the framework. We just, you know, worry about clue of the problem, about identifying business need of our customer. But of course, there's some work. But one of our goals in AI Sprint and KPIs actually was to be able to switch between one pipeline to another one fairly easily and quickly.
All right, thanks very much. I see Edward nodding on this too. Edward, one thing that struck me when you were speaking was the efficiency. Now, it wasn't just efficiency, technical efficiency, but it was the efficiency of the entire process of not having to shut down things because revenue is lost just when you're shutting down in order to do things. Is this something that is specific to wind turbines, or are you going to see that in other applications too, like the ones you talked about?
Certainly, you're absolutely right, John. I mean, if you think about power transmission line, yes, and you're going to inspect the power transmission line, you're going to switch off the entire power transmission line. If you're going to have a manual operator go up to an electricity pylon, climb up and have a look at the insulator. So although some insulators are inspected actually with use of a telescope from the ground, as you can well imagine, that is probably going to give you some kind of an idea, but it's not very accurate. So it's definitely the case that there are going to be various utility infrastructures that are going to be critical if you're shutting them down. The telecom towers is another one, perhaps less so, but if you think about a telecom tower, that is actually a strong microwave or effectively a radio frequency, which if you come up to it too closely, you're not really wanting to do that. So people who are going to be inspecting telecom towers are also likely to want them to be shut down for the period that they're going to be doing their inspection. You can imagine that a offshore wind turbine, again, to get to it is physically, you have to get on a boat, you have to go out into the water, which is potentially a day's trip to get out there. Then you're going to basically go and see maybe 100 towers out there, but you're going to go and be able to do 3 or 4 per day because it takes probably about 2 to 3 hours. You actually have to go up to the thing. You have to physically get inside it, unlock the door, shut down the turbine, lock the gearbox into position in order that the blades are not moving around, because you don't want them to be moving while you're taking your drone up there, because the drone will be damaged if it's going up too close to the blades. So all of this is time, and it's all effectively, if it can be saved, if it can be done faster, if the automated flight can be done, the accuracy of the flight is critical as well. And we've already talked about the need to repeat visits if there's a fault that we didn't properly identify in the first flyby, and you need to do a second flyby. And by the way, the other thing that's interesting, we talked about 20 to 30 categories of faults.
Exactly.
You know, that's another thing that I'd like to just take a second on. There's a huge debate about what is a fault. You know, am I looking at a squashed mosquito, or am I looking at a piece of oil, or am I actually looking at a crack, or what am I looking at? And you know, you're looking at a two-dimensional picture that sometimes is not easy to identify. And therefore, when you actually end up trying to get your AI to identify one of 20 to 30 categories of fault, there's a big discussion going on. And in some of our clients, what they've been saying is, look, don't even give us the 20 to 30 categories. Just tell us that there's a fault, and then we'll have our guy look at it. Because if you are identifying a fault for us, our guys know what they're looking at, because they've been doing this for years and years. And therefore, we don't want the AI software to second guess it. What we really want you to do is to identify that there is a fault, the location of the fault, and then give it to us so that we can actually then have our expert. Now, we've also clearly said at this point that this AI is really to be an efficiency factor. So ultimately, pretty much everybody ultimately says the AI is there. It will provide us 95% efficiency factor. We still probably want every one of those images to be re-looked at by a manual person. But now he's not looking at 1,000 images per turbine, but he's only looking at 10 images per turbine, and that is a huge factor. I don't know if you've ever seen at an airport where there is a luggage checking machine as we all pass through security. Those guys at those terminals, they get to have, I think, no more than about a half an hour shift. And the reason for that is the mind just blurs out after a while. You know, if you're going to be looking at 1,000 images, and you basically going to be doing that day in, day out, I could absolutely assure you you're going to be missing the errors, because your mind is blurred and you basically are no longer able to detect, because you've just you know, it's vision fatigue, basically what it is. So that's why, again, the AI, which can now spot that image and bring it up for, okay, now you're only going to be looking at 5 images as opposed to 1,000, then you can again imagine that that improves the accuracy of the whole process.
Yeah, that's very interesting. The AI does have this problem of false positives, so to speak, where the false classifications. And basically, you have a very interesting twist on it where you say, don't bother to try to classify, just let us look at it. Now, we do have a question from the audience from Florin, who's asking, and whoever, Michał or Edward, you want to answer this. Have you explored solutions that would not require to shut down the turbines?
Well, the answer to that, of course, is yes. And but think about it. A turbine blade at the end, I don't know if anybody has actually ever taken a guess at it. The speed of the turbine blade at the end of the 120-meter blade is well over 200 kilometers per hour. A drone, you know, you've got a drone and it's going to be sitting there and it's going to be blown out of its position with a 200 kilometer per hour blade spinning by. Obviously, the closer you get to the nacelle, the effect is less. but the longer the blade, the faster it's spinning at the end. Now, yes, you could potentially take a general picture and then freeze the frame and look up and down the frame to see whether, but ultimately, if you want accuracy, that's not going to work. Michael, over to you. You've experienced that.
There were attempts to do some high frequency videos of the blade, but it can work close to the nacelle indeed. However, at the tip with that speed, simply it's impossible. And there are the most important damages, also because of the speed. Simply, if something hits the blade close to the tip, the damage is much higher in that point. Also, it's exposed to lightning strikes. So the most dangerous damages are located close to the tip, and that's the place where you don't really have means to analyze that properly without stopping the blade. So,
yeah, I can see that. I suppose that would very much matter on the domain in which you're operating. If it's a high power line, you may have to shut it down because you may electrocute the drone. If it's a bridge, maybe not.
Oh, well, with power lines, you can do a lot of analysis with the drone, with all the security constraints. And also it depends on the type of, like with insulators, you are taking the pictures either infrared or the normal light, also in UV actually, because then you see the corona effect at the insulator. So you can have some information. You can also analyze sometimes there are inspection that actually covers the lines itself to check whether the trees are coming into the lines or things like that to make sure that the lines are safe. And this is of course different type of drone and different type of issue to be resolved. But simply there are a number of ways how you can analyze the power lines, for example, without disabling it. It's easier with the drone than with the human when he needs to climb up. With the turbine, you have the same issue. I mean, both the drone and human cannot actually do the inspection properly when it's running.
Yeah, let me.
John, I'll just kick in one other thought that we haven't talked about much, but it's certainly one that's important, is multiple cameras. Because we talk about, really, when we talk about images, we're talking about, we're talking about a color camera. But Michael has correctly said, if we're looking at power lines, for example, which the insulators get hot because they've essentially got leakage, you may be wanting to put an infrared camera sensor on there as well, or you may want to be looking at the corona because it's essentially spraying high voltage around because it's leaking as a high voltage has broken down. So there are multiple sensors that you can put on there. And obviously, if we start looking at military applications and so on, you get into even more complex sensors because there are other things that you're looking for.
And security, I suppose, too, if it's military. Yes, yeah. So, Michał, what would you say are the major challenges that in the research sense that you are confronting right now? Is it managing the continuum, or is it working on inferences, or where are the problems where are your pain points?
Well, at the moment with the wind turbines and what we are doing, what is actually challenging is indeed, being able to easily and seamlessly work between the components. I mean, if you're only in the cloud, inference is fairly straightforward thing. When you want to have the pipeline being split into multiple types of resources, being managed, monitored properly, dealing with the lack of communication, dealing with the changes in that infrastructures, especially if it needs to be dynamic, then the problem becomes really complicated. And I think that's from our perspective as a use case partner, when we want to have some working solution, that's actually the main focus right now, and the things that we are worried about or trying to resolve. So making that complexity manageable for us.
Yeah, thanks very much. Now I'd like to pass the floor to Rita, who would like to speak a little bit to the audience, so to speak. So Rita, can you say
yes. To us? Hi, good afternoon, everyone, and thank you, John. So actually, we would like to conclude this webinar also by asking you to join, let's say, an interactive session. It will be done with a tool that is called the Mentimeter. I will also share my screen so that I will guide you through this. And for us, I mean, it is also a way of understanding how much experience you also have with any tools, let's say, that are related also to the maintenance of wind turbines. I hope that my screen is visible to you all. And what you actually have to do is to go on a website that is called menti.com. I'm also pasting it here in the chat. And then you have to type the number that you see here at the very top of the page. So 42131692. And after you are here, you can also share your experience. So if you have ever used machine learning models, in this case to perform maintenance, and if yes, in which area. After that, we also have other two questions, but we would really be pleased to hear something about this from you. Okay, so okay, so the first question is not, okay. So I believe that most probably the person has said no, has most probably used machine learning for other in other areas. So for example, it will not be for maintenance, but most probably in something different, let's say like in other for other purposes. Okay, so here we have also another comment, and this person said that they have used it for models themselves, okay, with drift detection. Okay, thank you. Any other inputs from any other from the audience? Okay, anyway, we will also leave this chat open. So if you would like also to add any other perspectives here, we will keep it open, and then we can also have a look at it later on. So I will now move to the next question that instead is more related on the work that you perform at your own organization. So here we are assuming that you're adopting AI models within your organization, also considering that the majority of people that we have today in the audience are AI developers. And in this case, we would like to understand what have been the most significant challenges that you have faced while obviously using AI models. Also here again, feel free to type in any reply. It is an open question, so you can you can actually write whatever you feel is relevant. Okay, so here we have different inputs, which is nice. Okay, the first one is about the managing of the life cycle, sorry, of inference pipelines. Let's say another example instead is about the computational power that is required to train the AI models. And another one is for fighting with hyperparameters tuning to obtain high accuracy values. So anyway, I see that here you are using it. Let's say you have faced different types of challenges, most probably some of which are also shared by our use cases. And now I will ask you the last question, and then I will pass the floor back to John. So again, here we're also assuming that you're using AI models. And in particular, we would like to understand, since you are incorporating AI models into your organization, what notable improvements you have observed. So while in the other question, we were asking you about challenges, in this case, instead, we would like to understand what are the benefits instead that you have discovered, let's say, that you have gained thanks to the application of AI models. Again, here you can just type in your reply. So one is about receiving more stimulated feedback. Another thing is about automation. I suppose, even though no one has typed this in yet, most probably some of the benefits are also related to efficiency or cost reduction, as also at Michał before we're sharing. So with this, Oh yes, so now we also got a feedback about the cost. So they have reduced the cost, and in this way they have also improved the business process. And in this way, they also, let's say, discover many more scenarios that without AI could not be faced. So then here we have also a benefit in terms of efficiency, I would say. So I will now stop my sharing. As I said, if you would like also to share any other inputs, feel free, because this Mentimeter chat will be open, and then we will also gather your inputs also to receive, let's say, stimulating insights also for future webinars that we're going to organize. Thank you.
Thank you very much, Rita, for this. So we've now come close to the end of our webinar. I would like to ask Edward and Michael if you have any final comments. What are your plans? What's coming up next for you? What are the next plans? AI Sprint is not over yet. So what is next? Michał?
Yeah, well, it's not yet over, AI Sprint.
Exactly.
But, so we still, well, the closest challenge and most interesting part, I think, will be actually flying the drone with all the things that we built and seeing how it works in practice. That will be definitely interesting. And later on, we'll see. Hard to say right now. We have still a few things happening regarding the drone based calculations and drone projects, not only related to inspection, at least not in this particular sense, but so things looks interesting. Yeah.
And Edward, what about you?
Well, the good news is that we did have some commercial discussions with some of our customers that have already adopted some of the things that we initially provided to them. And they told me that we are very much in line with some of the things that are being done with AI Sprint along the problems that they are seeing today commercially. They all recognize this onboard processing and the amount of work that can be done on the drone, which means that you've reduced the cloud communication requirement. That is something that is definitely very sought after because it reduces the communication cost and the requirement of better infrastructure to be able to do on real-time data collection. But the second issue is this cross usage. Now, I think the one thing that we didn't spend very much time on, and I think it's just worth maybe going back and taking 2 minutes on, is the discussion about how do we actually identify faults or data, which
Indeed.
is the collection of data, because the AI can only do what it does based upon what it knows in its library. And if we're going to be going into other infrastructure, what we actually have to do is to create a library of images for each of the tasks that are going to be given to the drone. In other words, if we're going to be looking at church towers for some reason and seeing whether the cock at the top of the tower is in good shape, well, some AI images have to be taken, and maybe that particular rooster that is sitting on the top of that tower is going to be different on every tower. So maybe how do we know whether he's got his beak in the right position or not without taking those images? So Michael, you may want to just take a few moments a little bit about some of the improvements that we've made to make the cross industry work and how are we going to, because essentially if we go back to our beginnings, we needed what, about 10,000 images to be able to do anything sensibly with fault detection on a wind blade. And so those libraries were huge. Now, is there anything that we can do to optimize that is really the question that people are going to be asking.
Yeah, well, I mean, right now, we started quite some time ago, and to be honest, machine learning is changing in a very rapid speed. So things are changing a lot from where we started. Indeed, we took actually our library at some point had like 50,000 images. We started with 10,000 to get some reasonable results, and it went on and on. But anyway, of course, there are techniques to improve that situations. There are some. First of all, I mentioned that already, that we used some of the techniques to generate images. So GAN networks in particular, where we were either simply replacing the background using the same blade, or we were actually even generating the whole image, changing the style, trying to put the images on the blade as well. So there's a number of known techniques how to generate some synthetic data to improve your training database, especially that one of the issues which is very common in the machine learning world is data imbalance. I mean, some of the, especially for blades, usually you recognize like 5 severities of the damages, and first 2 are cosmetics mostly. Third, severity 3 is okay, it's pretty common, but still it means that someday when we stop the turbine, somebody will fix that, but it's nothing urgent. While in categories 4 or severity 4, it means usually that within 2-3 months you need to fix it. Otherwise you will really damage your blade. And category 5 is like you need to stop immediately. And you can imagine that number of examples of severity 4, not even mentioning 5, is very, very limited. So of course, getting data to recognize those properly and assess the severity properly, it's tricky. And again, techniques like I mentioned for generating the data or mixing up the data you have are helping. Also, there are some unsupervised methods that we are using sometimes in some applications, like simple segmentation. I mean, in case of erosion, it works pretty well. For example, semantic segmentation. But I'm not saying about training the machine learning models, but simply doing some KNN or some other methods for clustering the data. So there's a number of techniques. Which ones work best depends on the application. I know that for example, for insulators, it's very common to actually have multiple types of insulators in different states being simply put into the image, like combined with the background, just to train the models properly. So there are techniques, there are tools for that, there are tools for generating data, there are tools that help annotating the data. I mean, the effort we put into annotating the data is huge, enormous, to actually have all the data properly annotated, especially that this aspect that Edward mentioned is very important, that it's really difficult to say what kind of damage it is. And it's not only because you cannot see that, you can see what is it, but how you describe that depends on the approach, on the person. So you can, for example, identify the source of the problem. So, okay, there was a lightning strike that caused that damage, but you can also judge on the effect. So, okay, because of the lightning strike, I have delamination, or I have something else. So simply the cause or the result. There are different ways you can categorize things. And if you take the databases that are already annotated by different people in different ways, suddenly there's a mess in your model. So curating the data, generating the data, annotating the data, all of that requires some tools. And of course, there are tools for that, and they are better and better. And sometimes you don't need to even develop your own tools, but use tools that are available on the market or in projects like AI Sprint.
Well, Danilo, would you like to say some closing words on AI?
I don't know. I think, I mean, it's exciting, as I mentioned. We are looking forward to really run the stuff on drones in the real field to get some feedback. Probably in the beginning, everything will be broken, I know. But we are at this stage, and we have still 6 months to finalize our work. So, I mean, I think we are really touched. Really thank you all for the discussion. It was really, really interesting, and really, please again follow the next webinar. One more is planned for the farming photo tool in a few months, and really please follow us on and join our alliance. So that's really all from my side, and thanks for everybody to participating to the webinar. Thanks
from my side too. Thanks to all of you, Edward, Michał. It's been great. It's been a very exciting webinar, actually. All the best to everybody. The recording will be available and the presentation. So have a great end of the day. Bye, everybody.
Bye.
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 Thank you, John.